Let's take some example here. A very known molecule we just discussed before. We use it also in other components when we're dealing with Lewis structure, for example. Let's say we take SO4, 2-, which is sulfate. Very important, very heavy thing here. Sulfate, very important anion in marine environments. We see that. We'll see that when we're dealing with metabolism in the next lecture. And if you want to have the oxidation state of sulfur in sulfate, we need to, for doing that, having a couple of very simple rules. When defining oxidation state, there is a couple of rules. First, H, we have seen some example, but as an oxidation state of +1. Oxygen as an oxidation state of 2-. Those are more or less the rule. The other rule is an element when it has a compounds, like iron, for example, solid iron, solid sulfur, when you have sulfur as a component precipitating, the charge of this element is 0, doesn't have any charge. So the oxidation state of a solid is 0 by definition. Okay, so that's our really simple rule. Let's try to go back to our sulfate molecule and define the oxidation state of sulfur. Oxygen, by definition, is having an oxidation state of -2. Okay? So, in this case, we have 4 oxygen. So 4 times -2 will be equal to -8. So to understand now the next step, why don't we draw a Lewis structure for SO4? We did that a couple of times already. So SO4, we're going to do that rapidly. SO4, 2-. We will have both are in group 6, so we have 4 times 6 is 24 for oxygen, plus 6 electron for sulfur, that is 30. I'm not going to use those -2 charge yet, because I want you to think about the oxidation state of sulfur within this molecule. So we have the sulfur in the middle, then we have the oxygen, the 4 oxygen here, okay. We have 8 electron in the bond, we're adding the full octet around the oxygen. That will we have 6, 4 times 6 is 24, and then we have 24 plus 2, 4, 6 plus 8, 24 plus 8 is 32. We need to have a full octet around the sulfur. Remember the formal charges, so as we did last time, we will grab those 2 electrons here and grab it here, make a double bond, and here make a double bond. With that, we'll have a full octet around the sulfur. 1, 2, 3, 4, 5, 6. We'll have a full octet here because we are 1, 2, 3, 4, 5. This one will be a full octet for oxygen. This one will be a full octet of oxygen. And those here will be not a full octet, it will be a -1 charge and -1 charge for those 2 oxygen. That means that the entire molecule is -2. Okay, this is what explaining those SO4 2-. If you look at the charge, the formal charge of those different components within these molecules, okay, I'm going to use a different color here. Let's say green. This sulfur as a full octet, it has 0. This oxygen as a full octet, it has 0. This as a full octet, it has 0. And this has 7 formal charges. It should have 6 because it's in group 6. So he has +1 and +1. So if you look at this theoretical way of looking at those different elements or bond as ionic bond, if all the electrons are grabbed by the more electronegative elements in the molecules, which is oxygen, oxygen in this case here will grab those 2 electrons out of the sulfur. That means you will have -2 electrons for the sulfur. Those 2 electrons here will be grabbed by the oxygen. That means we'll have another -2 here. In this case, the sulfur here will lose 4 electrons already. So in terms of charge, it will be +4. And in this case, only 1 electron now is grabbed by oxygen. This oxygen has already 1 electron too many. So we will only grab this single bond out, meaning this will be -1 and -1. So at the end, what we'll have here is, for entire molecules, oxidation state of the sulfur will be 2, 4, 5, 6 plus 6. It will give 6 electrons to the surrounding oxygen. I'm repeating myself here. This sulfur will give 2 electrons to this one, 2 electrons to this one. 1 here and 1 here. Okay? So if you think about those elements as giving away electrons, sulfur is only giving 6 electrons out. In this case, the oxidation state of sulfur in sulfate is +6, is highly oxidized. But you understand, in the periodic table, sulfur has 6 valence electrons. So in this case, sulfur is giving away those valence electrons to the oxygen that is more electronegative. Let's do the same for H2S, which is hydrogen sulfide, a very famous gas in marine environments. When we'll see that when we're doing sulfate reducing activity, the reduction of sulfate is giving you H2S. What is the oxidation state of sulfur in H2S? We know by definition that H is having a charge of +1, so we have 2H plus, that means 2 plus 1. That means the S has to have a charge of -2. In this case, the electronegativity of sulfur is higher than the electronegativity of the hydrogen. That means the sulfur will grab the electron out of the hydrogen to complete the full octet. So in HS, in this case here, the sulfur will grab those 2 electrons here and have an oxidation state of -2. So in this case, because the sulfur is getting electron, this is a reduced form of sulfur. So if we have sulfate in one hand and H2S on the other hand, the oxidation state of sulfur in sulfide is -2. The oxidation state of sulfur in sulfate is +6. You have 8 electrons in between. A huge difference here. Here sulfur is giving away all the electrons, and here sulfur is grabbing 2 electrons out of hydrogen. And this is very important for metabolic purposes, because those electrons, as you know from electricity, can form currents and energy. That we'll go back to that a little bit later. Let's do another example. Carbon. Carbon has 4 valence electrons. Group 4, we know that. What is the oxidation state in pure carbon? Solid carbon. Could be graphite or diamond, for example. The oxidation state of carbon in those 2 elements are 0, because they are single elements precipitating of carbon, and by definition the oxidation state of carbon in a solid is 0 as pure carbon. What is the oxidation state of carbon in CO2? By definition, oxygen is 2 minus. You have two of them. That means if oxygen is way more electronegative than the carbon, it will grab those electrons. Again, this is hypothetically. Of course, they will share electron because it's a covalent bond. But as a way of seeing it, as a simplification, because oxygen is more electronegative than carbon, it will grab those electrons. Those electrons will leave the carbon. The carbon will be, in this case, oxidized, and the oxygen will be reduced. So in this case, the oxidation state of carbon in CO2 will be equal to 4 plus. Again, carbon is oxidized because it's giving away the electron to the oxygen. So we're talking about an oxidized form of carbon. What about methane? Very famous gas. H has by definition a +1 charge. You have 4 of them. That means the most electronegative element is the carbon in this molecule here, so it will grab electron. So those 4 electrons from the H, from the hydrogen, will be grabbed by the carbon. And carbon will be reduced. And the oxidation state of carbon will be, in this case, 4 minus. And it will be a reduced form of carbon. Very important for the carbon cycling. We'll see that later. So if you go from CO2 all the way to methane, you have an oxidation state of +4 here and -4 here. Also 8 electron in differences. In this case, carbon is giving away electron to the oxygen. In this case, carbon is grabbing electron from hydrogen. So again, you understand that if you are not at all electronegative, you don't have any affinity for electron, you will give your electron away all the time. If you have a strong electronegativity, such as fluorine, chlorine, you will want to grab those electrons all the time. If you are in the middle, you will act as a function of the element that are with you in your molecule. If the element that is with you in your molecule is more electronegative, you will give the electron, you will be oxidized. If you are more electronegative, you will grab the electron and be reduced. And you can so theoretically see in every molecules the oxidation state of every component. Knowing a set of rules, oxygen is -2, hydrogen is +1, a pure element is 0. I'm just going to illustrate this case, this rule, and the exception to the rule by taking a substance called H2O2, hydrogen peroxide. Hydrogen peroxide. Peroxide. This is what you're using to bleach your hair if you want to turn blonde, for example. And this is what is the oxidation state of oxygen in hydrogen peroxide. If you draw the molecule, it will look a little bit like that. In H2O, we know H is +1 and oxygen is -2. The rule is pretty simple. In this case, you have 2 hydrogen, hydrogen is +1, and oxygen, you have 2 oxygen. Those elements are 2 oxygen. They have the same electronegativity. They will share the electron. Nobody will grab electron from each other. So the only electron that will be grabbed by oxygen will be this one here for this oxygen, and this one here for this oxygen. Meaning, oxidation state of this will be -1 here and -1 here. This is one of the exceptions for oxygen. 99% of the time, oxidation state of oxygen will be -2. In some cases, it could be -1, as in hydrogen peroxide. Another cool example is this molecule, better refer OF2, which is oxygen difluoride. Alright. And why it's so cool is, now you understand. You look at the periodic table, which one of those two elements is more electronegative? You know that this is fluorine. Fluorine is the most electronegative element of the periodic table, so we'll grab electron out of oxygen. In this case, what is the oxidation state of oxygen in fluorine? It will be +2. Fluorine will be -1 or -1 here. So again, in oxygen fluorine, oxygen is 2+ and the fluorine is -. So another very rare exception of oxygen. This is to illustrate that always look at what element is the most electronegative in the molecule, and this element will grab the electron. Now let's have a look at the transition metal. Those elements we spend a little bit of time defining here. We know that they have this cloud of electrons, and they are not really attached to those electrons. They are really willing to give those electrons away. So they can have a lot of different oxidation state within the molecules, and it can be very complex. But let's take an example of a very known and very famous metal, the iron. So the iron is the argon plus, you're filling the 4s orbital with 2 electrons, and then you have the D, the 3d orbital with 1, 2, 3, 4, 5, 6. We have 6, so 6 electrons in this d orbital. So theoretically, you can share 6 electrons. You can give 6 electrons away from your d orbital. So an oxidation state for iron could be +6. It's actually, you can find iron in this oxidation state, but it's very rare, very rare. The two most oxidation state will be +3 and +2. So let's have an example of various minerals that you can find in geology, in the lithosphere. One would be iron oxide, FaO, if you want. Minerals that can actually have this formula is wurtzite, another element would be Fe2O3, very famous, we call that hematite, and Fa3O4, which is magnetite. Magnetite, if you know the name, it's magnetic form of iron in nature. So what would be the oxidation state of those three forms of iron in those three different molecules? In wurtzite, you know by definition oxygen is -2, so iron will be having an oxidation state of -2. In hematite, we have 3 oxygen, 3 times -2, that means -6. You have 2 iron, that means the iron is under 3 plus. Tired a little bit. It's of course oxidized. Okay, so if we stop here, in those molecules, if you follow the rule, both iron are oxidized by the oxygen, because oxygen will grab an electron, the electron from the cloud of electron from the transition metal. But this one has less electron than this one. So this one is more oxidized than the other one. So this one is what we call a reduced form of iron. It is a bit confusing because both in the molecules are oxidized. They're giving away electron. But if you compare those two, one is more oxidized than the other one. One is called the ferric iron when it's oxidized form of iron, and this is a ferrous iron when it's reduced. So this ferrous iron is found in absence of oxygen, O2, molecular oxygen. When you have molecular oxygen, you're forming this ferric iron because the ferrous iron will give one extra electron to the oxygen. What is the oxygen state of iron is in magnetite? This is a tricky one because you cannot have a simple rule is Fe3O4. But if you want to understand that, you can simplify this by having Fa3O4 equal FaO plus Fa2O3. So what you have here is a combination in single minerals of a reduced form of iron and an oxidized form of iron in the same minerals. So in this case, this would be 2 plus, 3 plus in this case here, and 2 plus. So this is an exception. This is a very cool mineral, magnetite, that has in the same crystals both forms of iron, the reduced one and the oxidized one.